Hi folks, today we are going to continue studying the system of 2 degrees of freedom of the small oscillation for a system of 2 degrees of freedom. But this time, instead of using the Euler's forward method, we are going to apply the Heun's method, which is a nice improvement to the Euler's method. We discovered yesterday, in the past video, we discovered that the Euler's method predicts the maximum displacement of one of the mass 1, larger than its initial displacement. So, we concluded that this is not physically possible, this is not feasible, and because it defies the law of conservation of energy. So the reason that happened is because the forward Euler method is frequently unstable. The method tends to overshoot the position of the masses at each time step, and this error, can accumulate over time. Now, we are going to look at improved method for estimation of position of velocity. This is the Heun's method. Remember, let us remember our problem. Our problem is, the problem is this. Two masses, M1 and M2, they are connected by this spring, which has constant K2, and there is a spring here, and there is another spring here, K1 and K3. Yep. So let us see the problem. The two masses arranged horizontally are connected to each other by a spring, blah blah blah. As I just told you. The equation of motion are given as, remember, as the previous video. The acceleration of particle of mass 1 is x1 double prime equal to minus k1 times x1 minus k2 times x1 minus x2. And the acceleration of mass 2, x2 double prime, equal to minus k3 times x2 minus k2 times x2 minus x1. And the initial condition, x1 at t equals 0 is 48, x2 at equals 0 is equal to the velocity of mass 2 at time 0 equals 0, and the velocity of mass 1 that is equal 0 also. And we are going to assume that the constants of the spring's constants are equal to 2.9. First, remember, we transform the system of two ordinary differential equation of second order into a system of 4 first order differential equations using this nice trick. The trick is basically that we know that the derivative of the position of the mass with respect to time is equal to velocity. So x1 prime is equal to v1 and x2 prime is equal to v2. Then the coupled system becomes this one. x1 prime equal to v1, v1 prime equal to minus this thing here, x2 prime equal v2, and v2 prime equal minus k3 times x2 minus k2 times x2 minus x1. Now, let us consider the Heun's method. Well, in the Heun's method, look, we just let us do some nice. We can write this 4 equations into just one form, where capital Y prime is a vector which contains the positions and the velocity of the two masses. So the equation can be written, the first order system of equation can be written just like this. Derivative of capital Y with respect to time is equal to A, matrix A, times capital Y. And this can be, this here is this nice form of equation where the matrix A is this matrix times Y times 4 times 4, yeah? Square matrix. So you see that, for example, derivative with respect to t, the x1 is equal to this. You multiply this, all this term with this, yeah? And the only term we survive is b1. Here, derivative the x2 with respect to t, you multiply all this time, all these terms, which he with this vector, and the only survive is b2. And we see the same with the others. So, the vector f represents the right hand side of the ordinary differential equation, and for ease we will write this as this form. Capital Y prime equal to f of capital Y function of t. So let us explain what is the Heun's method. The Heun's method is an improvement of the Euler method. What is the improvement? Well, the improvement is basically that we are going to apply the Euler method first, but at how can I say, at an intermediate step. So we can calculate a value of the vector capital Y, I call it Y start, yep, evaluated at time n and time n plus 1. It is given by the application of the Euler method. Here, this is the Euler method. Capital Y at time at step n plus h multiplied or times f evaluated at capital Y n. But instead of this being the the solution of our problem at time after step n plus 1 is an approximation, and then we apply again the recipe is this one. The real solution in the method of Heun is to calculate y step n plus 1 equal to n plus n, y, capital Y, and time n, or step n, plus h multiply, sorry, this start multiply, I should delete this start, sorry, multiply by 1.5 multiply or times the function, the vector evaluated at times n plus the function evaluated at time n plus 1, which is this one. So, in this case, we have to apply first, that is very important, we have to apply the Euler method first. So the equation we got in the past video, we should apply here, and then here. But instead of being the solution, which is the case in using Euler method, in this case, x1, b1, x2, and b2 are intermediate steps for the real solution. The real solution is here. Look, x1 evaluated at t plus delta t is equal to x1 evaluated at t plus delta t multiplied times 1 divided by 2 times b1 at t plus b1 star at t plus delta t. This is the new approach of our solution. Using the same procedure for the velocity and the velocity here, the position here, and the velocity is here. We got, this is the new recipe, equations 8, 9, 10, and 11. So, again, knowing, or if we know the velocity and the position of each mass at time t, we can, using this nice recipe, we can find the position and the velocity of the masses at time equal t plus delta t. This is the improvement of the Heun's method. Let me show you now the numerical solution, the plots. This is very important, you can see. For example, the oscillation of mass m1. You know, in red is the position, in blue, the blue line is the velocity. In the vertical, the position and velocity. In the horizontal, the time, from 0 to 20. You see, the initial position is 48 and the initial velocity is 0. In this case, there is the oscillation of the mass, okay, right? But never, I'll show you in the next figure, in the other figure, never is going to be a position of the mass 1 larger than 48. And the velocity is also oscillating. Yeah, see? Let me show you now the plot for the other mass, the oscillation mass M2 using Heun's. Again, in red, line red, is the position, and in blue line, the blue line is the velocity. Both started at 0. Again, oscillation, oscillation. You see? But more importantly, let me show you the following figure. This is very nice figure. Look, this is the difference between the position of mass 1, mass 2, and the position of mass 1 at each time between 0 and 20. And look, the result is that the position, the absolute value of x2 minus x1 is never larger than 48. Of course, because the initial position of the system was 48. Yeah, look, the initial, x2 was 0 at t equals 0, x1 at t equals 0 is minus 48. And you see now that we obtained a nice pattern of oscillation, which means that the system, the energy, the kinetic, the potential energy is oscillating between the two masses, but never the total energy of the system is larger than the initial energy of the system. This is a nice result, and you see that the only addition to the method was to calculate intermediate step. This one, the start term. So I hope you will find this helpful. But if you need more help or need more assistance, please, I will be glad to hear from you. Thanks.